Welcome back everyone. We're looking at more circle geometry and proof. We are looking at a particular theorem for what's called cyclic quadrilaterals. So polygons, as we know, are flat shapes with a various number of sides connected by straight lines. And they can be inscribed in a circle if all their vertices lie on the circumference of the circle. Okay, so no part of the polygon goes outside. Alright, so all the vertices, okay, each vertex lies on the circumference of the circle. Alright, and they don't stray outside. So if we know what inscribed means, we can then define a cyclic quadrilateral. So a quadrilateral, a four-sided polygon, that can be inscribed in a circle is called a cyclic quadrilateral. And here's a picture of one. There we see A, B, C, D in its natural habitat. Isn't it splendid? So, provided it is a polygon, four-sided, quadrilateral, and it's inscribed in a circle, it is cyclic. Okay, so the word concyclic is sometimes used. Okay, to talk about that. Okay, so concyclic. So it's got the vertices there on the circle. Nothing is extra of the circle. The theorem we're going to look at and then prove is that opposite angles in a cyclic quadrilateral are supplementary, alright, meaning they add to 180 degrees. So we're talking about two angles adding to 180 degrees. Okay, and so we can see ABCD is a cyclic quadrilateral given to us. Alright, so the symbol for this theorem too is that there. Okay, and so given that this is a cyclic quadrilateral ABCD, we can look at two angles ABC, which is this angle here, and angle CDA, which is that angle there, and they add together to make 180 degrees. BCD and DAB, which is that one and there, are also supplementary. So if we're given a cyclic quadrilateral, we need to determine that the opposite angles are complementary. Okay, so let's prove that. So the first thing we do is draw a reasonable cyclic quadrilateral. Okay, so it's inscribed in a circle there, a PQRS we've got. Now added to that, I'm going to put in a couple more lines, this radius, and I'm going to put in this one here too. Sorry, they should be straight. Now let's consider a couple of angles. So consider angle ROP and RQP, which are here and here. Now I'm looking at, when I'm saying ROP, I'm looking at the obtuse angle because there's also a reflex angle around the other side, which we're going to look at in a minute. So notably, that's the obtuse angle ROP. They're both subtended by the same arc RSP. So we're going to note that both subtended by arc RSP. Okay, so symbol for arc, the curve. Now if angle RQP equals some value A, as you can see in the diagram, then by theorem 1, alright, okay, then by theorem 1, see my previous video for that one, we've got that's the one where the angle subtended at the center is twice the angle at the circumference when they share the same arc, this is subtended by the same arc, which they are in this case, we can say that ROP, the one that we highlighted there, the obtuse one, alright, ROP is twice that A, so we can call it 2A. Alright, again, that's from Theorem 1. Consider also the reflex angle ROP, alright, so thus, and the angle RSP, which we can see there down the bottom there, and they're subtended both by the same arc, alright, which is RQP, this arc here. Alright, they're both subtended by that same one. So the ends of the lines that define them are standing on the ends of that same arc. Okay, so with that in mind, we can look at angle RSP again. Alright, which is that B. You could say let it equal B, okay. Then again by Theorem 1, this one, angle ROP will be twice RSP, so 2B. Remember, because the angle at the center is twice the angle at the circumference, okay, when they're subtended by the same arc. Now if we look at the center here, we've got two angles. The two angles at the center are the two ROP angles. One of these is obtuse and the other one is reflex, and they add together to make 360. Okay, and we said one is 2A and the other one is 2B. Okay, so the orange one is 2A and the pink one is 2B, and they add together to make 360. So 2A plus 2B equals 360 degrees. Thus, A plus B is 180 degrees. Now, we've got the answer we want here. That means those two angles are supplementary. Are they the angles we want? Are they opposite angles of a cyclic quadrilateral A and B? Are A and B the angles we want? Well, there's A, there's B. Alright, and so we do have opposite angles of a cyclic quadrilateral equaling 180, i.e. supplementary. Okay, just a concluding statement there. Okay, so yep, that has been shown. And just as a note, the converse works. Okay, so the converse, remember the converse is a logical process. If the original theorem was P implies Q, the converse is Q implies P. So the order is swapped around. So the second one implies the first one, okay, and it holds. Okay, so that would be if the angles of a quadrilateral are supplementary, then it is a cyclic quadrilateral, okay, instead of the other way around. So note that the converse is true for this theorem. Sometimes it's called Theorem 4, but like I said in my previous video, that's kind of nominal. Not everyone will call that Theorem 4. I mean, I've seen books that call it Theorem 14 or whatever, but I'm just carefully, like, you don't have to call it 4, but the opposite angles of a cyclic quadrilateral is also true in its converse form. Okay, a simple example to finish off, and we're going to find the pronumerals here, x, y, and z. Okay, and there's two ways we can do it. Let's start with an easy one, but we've got to find y. we've got a theorem we can use, okay, and again by this one, theorem 1 yet again, okay. We've got 100 there, and so 100 is 2 lots of y according to theorem 1. The angle at the circumference is twice the angle. Sorry, the angle at the circumference is half the angle at the center, so the angle at the circumference will be 50. So y is 50 degrees. Okay, and so again we can look at that theorem if we want. Okay, again by that theorem to find z, because they're subtended by the same arc. All right, so we're talking about this arc here. All right, we've got 100 is 2z, z equals 50 degrees as well. All right. Now, if we want to use the theorem we've just developed, you could say by cyclic quadrilateral. Okay, you deliberately make it not look like a rectangle on there, okay, because quadrilateral does not have to be a rectangle, okay, that's a special case if anything. So by that one, we've got, you've got a quadrilateral here, 1, 2, 3, 4, okay, and you've got opposite sides here. So we've got opposite sides of a cyclic quadrilateral are supplementary. We've got y already, so we can find that quite easily. Okay, so if y is 50, 50 plus x, so x is 130 degrees. Not too shabby, right? As a little note, you could also look at the other side, the reflex side of this angle AOB. All right, and you could use theorem 1 again, and if you like using theorem 1, well good, there's plenty of opportunities to use it. We've got 360 take 100, all right, so revolution take 100, okay, so sorry, that should be take 100 equals that reflex AOB, which is 260 degrees, and 260 degrees is going to be twice what x is, okay, because it's that theorem 1, it's just upside down, all right, to the typical symbol. So you've got like that, if that makes sense, all right, it's a bit like that. So twice the angle at the center, okay, compared to the angle at the circumference. So 2 lots of x will make 260, so that equals 2x, therefore x equals 130, and you can see that's what we got using the cyclic quadrilateral theorem. Okay, thanks for joining me, and see you in the next video.